Okay, good evening, everyone, and welcome. My name is Risa Wexler, and I'm the director of kipac, the Kavli Institute for Particle Astrophysics and Cosmology, which is an institute at Stanford and the SLAC National Accelerator Lab. I'm really pleased to welcome you to our first ever remote public lecture series, which we hope will help us share some of the wonder we have for the universe and some of the exciting discoveries we've been making, and provide some insight into some of the biggest questions that humans have ever had. Like many of you, we've been working from home since early March and having all our seminars and discussions online, and we've all been adjusting to new ways of working and communicating with each other. So like many things happening in these months, this event will be an experiment, and we welcome your feedback about how it is working. We're planning to continue the lectures every 2 weeks, and we will also post recordings on our website and YouTube channel in case you're not able to join us in real time. Before diving into introducing our speaker, I want to spend a few minutes acknowledging the moment we are in and the fact that a lot of members of our community and beyond are in pain, and that we're in a moment in which inequities and injustice in society are visible on a large scale. We have all been struggling with the pandemic's impacts, and we've also clearly seen how those impacts have had racial disparities in both health and economic impacts that are based in structural inequities and ongoing racism. And this week, we have been reminded again how Black lives in this country are subject to systemic violence. The injustice, inequity, and violence that are so vivid this week are not separate from the injustice that leads to racial disparities in who is welcomed into and supported into the physics community. As scientists at kipac, we are incredibly lucky. We get to spend our time thinking about big questions, about what the universe is made of, how things in it formed, and how they behave under extreme conditions, and whether there is life outside our solar system. It's an incredible privilege to be part of the set of people that are asking these questions and sometimes even answering them. And this privilege, both to understand and discover, should be open to everyone. So as we start with that premise that the universe is for everyone, that understanding how it works is one of the great joys available to humanity, we must also recognize who is missing, the potential members of our community who should have had the opportunity to understand the universe who are not here because of the ways systemic inequities and the past and present of racism in this country have excluded people, and the ways that this is related to the injustice and violence that Black people in America face every day. This pandemic has impacted so many of us, and we planned this series knowing that many of you would be in different circumstances, that many people who we would have loved to have join us would not be able to attend. And we are aware that that is even more true now as many in our community are fighting for justice. So with that in mind, I just want to pause for a minute to recognize the Black lives that have been lost in police violence this month and the lives lost in the pandemic. To recognize those who are not able to be here because they are doing the work of fighting for a more equitable and just society right now, or who are dealing with the consequences of the pandemic in their lives and in their communities. And also to recognize the potential members of our community who should have had the opportunity to understand the universe who have not been welcomed. And I hope that many of you will join me in working to reduce those barriers and working to enable every single person who is interested in understanding the universe around us to be able to join me in that endeavor. So with that, let me introduce our speaker. We are incredibly lucky to have Professor Bruce Macintosh as our speaker today. Bruce is a pioneer in optical instrumentation and adaptive optics, and in particular in developing the instrumentation that is needed to image planets outside our solar system. Bruce is the principal investigator of the Gemini Planet Imager, an advanced adaptive optics planet finder for the Gemini South Telescope, which over the last year has imaged the planets around more than 500 stars. He also co-led the team that took the first ever images of a system of extrasolar planets, for which he was awarded the Newcomb Cleveland Prize by the American Association for the Advancement of Science. And he's working with the newly named Nancy Grace Roman Telescope team to plan for the next generation of exoplanet observations. Bruce is also currently the deputy director of kipac, and it has been an enormous privilege to work with him in this role. So Bruce, please go ahead and start sharing your screen. And to the audience, let me just say that we welcome your questions through the during the talk. We're going to take them at the end. So please feel free to type your questions through the Q&A box in the Zoom. If you're on YouTube, you can do it through the chat window in YouTube or through the Google form that's been provided so that in case you're not signed in. So we'll spend time at the end of the talk going through these questions. So with that, let me pass it on to Bruce.
Okay, yeah, thank you for the introduction. And it is a extraordinarily challenging time to be doing something like this, you know, even planning it as Risa said, in the face of a substantial pandemic that we're all trying to navigate our way through and keep people as safe as possible. It's even enormously more challenging now when a large fraction of the people who are listening to this are undoubtedly under some kind of curfew, unable to leave their homes, a larger fraction who probably would not feel safe from the authorities if they did leave their homes. And it's odd from my position of comparative safety and privilege to be trying to think about how to discuss astrophysics. And so, you know, following on what Risa said, I would strongly reiterate that Black Lives Matter, that the way our society treats them matters, and that although astrophysics and extrasolar planets are important and fundamental questions, they're nowhere near as important and fundamental as the safety and dignity and equality of people in this country and beyond. And again, as Risa said, I think even within the context of our profession, we have a fair amount to answer for in our treatment of people in the past, ranging from minorities to indigenous people and beyond. And so, while we'll discuss astrophysics for the bulk of this discussion, we're certainly happy to take questions that move beyond that to the social context of science at the end, time and sort of collective dignity permitting, and recognizing that this is by no means an ideal time to be trying to do something like this. All right, and meanwhile, let's see how we can do on sharing one screen and getting the actual talk parts started. So, and I guess as a last thing, you know, people who've heard me give public talks before, I have some tendency to be somewhat flippant in the way I communicate things, which does not necessarily feel like the right response under current situations. So I hope you'll all be patient as I try to find an appropriate tone for this going forward. So, you know, though it is obviously not, as I said, the most important question in the universe, the question of the uniqueness of the world is one people have been thinking about for thousands of years. Philosophers 1,000 years ago, like Albertus Magnus, thinking about, do there exist many worlds or but a single world, at a time when the only world someone could envision was something like our own, a planet with life upon it. After thousands of years of thinking about that question, we're now in a point where we still don't know the answer to it, but we know how we can find out the answer to it, that the combination of technology and our understanding of the way the universe fits together has reached the point where we can address questions like, are there other planets out there with life, in a way that is rigorous and scientific, and that with the right resources we could choose to produce an answer to, if not in my lifetime, almost certainly in the lifetime of other people on this call. Going back even further, though, just to think about context, this is a sort of 2,000-year-old view of the universe. In that view, there was an Earth, and there were a bunch of things that were not the Earth, and everything else in the universe went around the Earth. We obviously had to be the center of everything, again, a viewpoint that many of us might consider in these recent events. How could we not possibly be the most important thing in all of what we considered to be a creation at the time? The problem with this viewpoint, aside from the fact that it's a sort of egotistical solipsism, is it also does a terrible job as science. If you assume the Earth is at the center of the universe and everything goes around with it, you do a really bad job of predicting, for example, the motions of the planets, where Mars is going to be tomorrow night or a week or a month from now. The planets don't move as if they were orbiting around the Earth. And of course, that was recognized by series of scientists and philosophers. Ultimately, the idea that we were not the center, but that we all orbited around the sun was codified by the combinations of Copernicus and Kepler and Tycho. Copernicus, who initially suggested that or promoted a model of planets going around the sun. Tycho, who was really an observer who produced huge volumes of precision data about the motions of planets so that models could be tested against it. And then Kepler, who in some sense was an astrophysicist, a person who generates models, who came up with the mathematical equations that let us show how planets move in their complex elliptical orbits around the sun, to the point where he could in fact predict the position of Mars and where Mars would be a month from now with greater accuracy than anybody else in history. And to a scientist, that was probably the most compelling demonstration that the old model, which didn't successfully predict things, was wrong. But the other compelling demonstration of this was another scientist, Galileo, one of the first people to take a telescope, though he didn't invent telescopes, and look up in the sky. And one of the first things he did was look at the really bright things, like, say, Jupiter, one of the brightest things you can see in the sky. And when he did, he saw 4 bright dots next to Jupiter. And then the next night, the same 4 bright dots in different positions. The next night, 4 bright dots in different positions. And he rapidly realized what he was seeing was an entire system of objects moving around, that Jupiter was surrounded by its own miniature planets. Now we realize, of course, that they're moons orbiting it in the same way that the other planets orbit the sun, in the same way that our moon orbits the Earth, that the Earth was no longer unique, that it no longer had to be the center of everything. And this combination of the quantitative astrophysics, but also the visual demonstration, really completed what we refer to in the history of science as the Copernican revolution, the dethroning of the Earth from the center of the entire universe. At the time they did this, there were approximately 6 planets known in our solar system. By today, for a while we had 9. Now we're back to 8 planets, kind of embarrassing to lose one, depending on how your classification works, orbiting around the sun. And as you look at them, you can start to see distinctions and differences in these planets. There are giant planets far away from the sun. There's small rocky planets close to the sun. I should say, actually, going back to Kepler, one of the other things that he proved, in addition to mathematically codifying how we orbit the sun, is he noticed, somewhat unsurprisingly, that the farther away you are from the sun, the longer you take to go around. So Mercury goes around the sun, in a quarter of a year. The Earth, of course, in a year. That's why we call it a year, all the way up to Neptune, that goes around to the sun in 165 years. But in any event, this picture of the solar system, its giant planets, its small planets, when I was in graduate school, was kind of well explained by the way we thought planetary systems could form. And I was pretty much taught that this was what every other planetary system would look like, that again, we had to be typical, that we had to be whatever process produced the Earth had to be a universal process that would operate everywhere else. And in some sense, that was a very pre-Copernican view, the idea that the solar system we live in, or for that matter, as we'll hear about in later talks, the galaxy we live in has to be the prototype, has to be the best of all possible solar systems. The process of discovering other solar systems over the past decades has proven that that's not actually the case, that we are not the archetype for what every system could possibly look like. A thing that's hard to show on diagrams like this is the scale of the solar system. So if my assistant will come and assist me, wherever she's wandered off to, we can try and do a demonstration of the size of planets to provide some context for other solar systems. So imagine, if you will, that the sun is a grapefruit. On that scale, Earth, nice typical planet, obviously very important to all of us, is roughly the size of the sesame seed, tiny compared to the sun, but not anywhere near as close to the sun as I'm showing. If the Earth was the size of a grapefruit, our sesame-sized Earth would be somewhere on the far side of my house, approximately 40 or 50 feet away. And so we'll place that there for reference. Jupiter, the biggest planet in our solar system, huge in the diagram I was just showing you, again, to scale for our grapefruit sun is roughly the size of this juniper berry or peppercorn. And the solar system is so large, Jupiter is so much further away than the Earth, that again, to scale, it would actually be somewhere across the street, where we will place it carefully for the remainder of this lecture. On that scale, the solar system is huge. The distance to other stars, though, is even more unimaginably huge. If the sun was a grapefruit, the Earth is the sesame seed in our back bedroom, Jupiter's across the street. The very nearest star, which is actually surprisingly near by astronomer standards, is currently somewhere on the East Coast of the United States, where we will not attempt to place another grapefruit because it would be complicated to do that for purposes of this experiment. And given those incredible distances between stars, it's not surprising that it's very hard to tell if that grapefruit on the East Coast has another peppercorn, let alone a sesame seed, orbiting around it. But that's what astronomers have learned to do over the past 20 years. To start with, we didn't do it by seeing the peppercorns. The first technique we used to study other planets around other stars, was by seeing their effects on the stars themselves. And the biggest effect is gravity. If you consider a planet orbiting around the sun, it does that because the sun's gravity pulls on the planet, but the planet has gravity too. And so in fact, the sun orbits back. The two of them pivot, they dance around a point in between them that we refer to as the center of mass of the system. They move very slightly. That center of mass is inside the sun, but it's not at the center of the sun. So even as we speak, the sun is wobbling due to the gravity mostly of Jupiter and to a lesser extent Saturn and the Earth, and an even lesser extent the other planets. And even if you couldn't see the planet, which normally you can't, though I'll talk about how you can later, that wobble would be detectable, that tiny motion of the sun. It's about a brisk running pace, the motion we induce by Jupiter, but we can measure that with instruments called spectrographs, instruments that take the light of a star that split it up into its individual wavelengths, because that motion shifts the wavelengths of light. When the star is moving towards you, the light from it becomes very slightly bluer. When the star is moving away from you, the light becomes very slightly redder. And we can measure that tiny change in color, that motion, with our spectrographs. And that was the first way extrasolar planets were detected by Mayor and Kalos, who were awarded the Nobel Prize recently for this discovery. And when these planets were detected, it was an enormous epoch-making result. There were a lot of exciting press releases. There were beautiful artist conceptions like this, showing a giant planet close, orbiting its star with a moon that appears to be evaporating for reasons I'll talk about in a second. But of course, we know none of that. What we know about these systems is just that their star is wobbling. We plot that as a graph. I won't show a lot of graphs, but here there is a plot showing the motion of the star, its velocity versus time. And that tells us two things. First, how long it takes the star to wobble, the duration of that orbit, tells us how long it takes the planet to go around. Every time the planet goes around once, the star goes around once in the opposite direction. And for these first objects, it was about 4 days. And secondly, how much the star wobbles tells you how big a planet there is compared to the star. If you have a big planet and a small star, you get a lot of wobble. If you have a small star and a big planet, its gravity can't pull it much and you don't get much wobble. The astonishing discovery, the astonishing thing about this initial discovery of planets around other stars is that they went around their star not in 12 years, like Jupiter does in our solar system, which is pretty much what everybody expected, not in 1 year, like Earth does in our solar system, not even in 90 days, like Mercury does. The first extrasolar planet discovered went around its star in 4 days. From Kepler's laws, to make it all the way around the star that quickly, it's got to be extremely close to the sun. But it still produced a huge gravitational wobble. It still was an extremely massive planet like Jupiter. And in our kind of peppercorn coordinate system, stop the screen share to show it a little more carefully, it would literally be about this far. So not across the street like my earlier peppercorn planet was, not even in the living room like Earth, practically by astronomy standards touching the star that it's orbiting around. There we go. After that, a bunch more were discovered fairly rapidly and efficiently. showing a significant number of solar systems that really looked nothing like our own, that had these giant planets orbiting close to their star, that somehow whatever process produced the Earth didn't have to be universal. Though it still could be common. These giant planets were actually surprisingly easy to find, so we found a lot of them, but they're still pretty rare. Only maybe a few % of stars have what we call hot Jupiters, Jupiter-sized planets skimming the surface of their star. The second way people have studied extrasolar planets is through their shadows, still not seeing the planet itself. If you happen to have a planet orbiting around its star, and you look at it from just the right direction, so you're seeing it from the edge so that the whole system is lined up pointing it as us, the star will eclipse the planet for a tiny period of time. It will pass in front of it and block the planet, excuse me, will eclipse the star. I always get that backwards, for a small fraction of time. And during that small fraction of time, even if you can't tell there's a planet there, the star will look a little bit dimmer. Planets, turns out, are opaque, they block light. And so the star will get, for a planet the size of Jupiter, about 1% fainter than it was before. And 1% fainter is actually something we can measure easily. You can literally do this with a backyard telescope and a decent camera. Modern digital cameras are precise enough to make those measurements in a straightforward fashion. It's not straightforward if the planet is small. If we're back to the sesame seed sized planet, it only makes the star a tiny fraction of a % fainter. And of course, you have to get incredibly lucky. You have to line up so that you're looking at it not from above like this system, but so you're looking at it from edge on so that you see that eclipse as the planet drags itself across the star. But if you do so, you can detect a planet. Since getting incredibly lucky is not really a practical strategy in science, the way to be successful in this is to look at a lot of stars. And the most successful example of this so far is a NASA mission called Kepler, a space telescope, medium-sized, 1 meter, not a huge telescope, but with an enormous camera, hundreds of megapixels, letting it look at a huge fraction of the sky in the constellation of Cygnus, so it can monitor 100,000 stars at once and see if any of them happen to have planets passing along them, if any of them happen to be lined up just right. You still have to get incredibly lucky. It's been calculated that if every star in our galaxy had a solar system just like our own, with all 9 planets, only out of the 100,000 stars Kepler looked at, it would have discovered a total of 3 planets. Kepler did not discover a total of 3 planets. It discovered almost a total of 4,000. These are a fraction of the systems, just the interesting multi-planet systems that it discovered in a video put together by Ethan Cruz. Over in the right is our solar system. You can see by comparison how spaced out our solar system is with its planets. All these other systems have several, up to half a dozen or more planets crammed in close to them, bigger than our Earth, smaller than our Jupiter. Hundreds and thousands of planets that we refer to, largely because we're not that imaginative, as super Earths. And again, on my scale diagram, they would kind of go here. And it turns out that may be the most common kind of planet in our galaxy, and not a kind of planet we have any equivalent of. And again, when these were discovered, there were press releases. Some of the planets it discovered were in what we refer to as the Goldilocks zone, the place where it gets just enough sunlight from its star that in principle it could have the right temperature on it for liquid water, shown by this shaded region surrounding the star here. Kepler 186f, we're not very good at naming these things, was one of the first examples. Press release had this beautiful picture with sort of clouds and maybe hints of continents. It looks like it's got some ice caps because they drew it as a relatively cold planet. Headlines tend to talk about discovering another Earth. But again, that's not what we know. What we know is just there's a planet there. We know how big it is. Could be a planet like Earth, could be a planet made out of rock. It could be a planet made out of something completely different. We are starting to be able to study the composition of planets using something called a spectrum. If you take light from something like a cloud of gas and spread it out through a prism, you get a rainbow, as you do as you spread out any light through a prism, but with a pattern in it. Every substance in the universe emits particular colors of light and doesn't emit other colors. The combination, those what we refer to as spectral lines, are like fingerprints of individual atoms and molecules. And so by studying those fingerprints, looking at a spectrum, you can actually tell what an object is made out of without having to touch it. For the transiting planets, for the ones that we discover by blocking their starlight, we can do that if everything lines up just right. If you have a giant planet blocking the light from the sun, Some light from the star, like this top ray, will make it all the way to you. A lot of rays of light will get blocked by the planet. Planets are opaque. A few rays of light, a few poor photons, will graze the planet and pass through its atmosphere. And by analyzing those rays of light, you can tell roughly what the atmosphere is made out of. Right now, we can only really do this, even with the Hubble Space Telescope, for planets that are very close to their star, preferably planets that are giant. And so those planets are hot, they're not going to have life on them. And what we discover are things like hydrogen and carbon monoxide and water and helium in their atmosphere. But there is the prospect, if everything is really lucky, that we'll discover a few planets that are like Earth that still transit their star, that are close to small stars, which makes them easier to discover. And then the James Webb Space Telescope, which I won't be talking about, might be able to measure the composition of their atmosphere. But what I will be talking about is the third way we study other planets, which is currently really the hardest. And that's actually taking a picture of a planet, actually looking and seeing, like Galileo did, the planet as its own distinct point of light. Why don't we do that all the time? It's really hard. Not only are planets the juniper-sized thing somewhere across the street, this grapefruit is glowing, literally 1,000,000 times brighter than the amount of light that a planet reflects or gives off. The metaphor we usually use for this is it's like looking at a lighthouse to try and see a firefly next to it. And in fact, Kate Follett, a scientist I work with, did the calculation to show that basically the planets that we've managed to image so far are basically the brightness of a firefly. A planet like Earth wouldn't even be a firefly. It would be like seeing a single cell of bioluminescent algae next to an extremely bright firefly lighthouse from miles and miles away. Planets are lost in the glare of the star, especially if you take a look at them from the surface of the Earth. The Earth has an atmosphere. Atmospheres are complicated things. They're nice because we can breathe them, but they distort rays of light. They make rays of light from the star go in different directions. This movie you're seeing is an image of a star that should have been a single sharp focused point from a telescope seen from the Earth's atmosphere, through the Earth's atmosphere with a reasonable sized telescope. So everything we look at is blurry, which makes it incredibly hard. If there was a little planet next to the star, it'd be completely lost in this blur. As another example, here's an image of the planet Neptune as seen from the Earth. You can kind of tell that there's a planet there and that it's somewhat round, but not any more than that. But we can fix that. So a technology that was developed more than 20 years ago is something called adaptive optics. That corrects for the way the Earth's atmosphere blurs images of a planet. You take a telescope, focus light from the telescope down, not onto a camera, but onto another mirror, a thin glass mirror that can bend, that can change its shape hundreds or thousands of times a second, sharpening up all the distorted rays of light. You have a sensor that measures how it's been distorted. You have a computer that connects them. And then finally, a science camera that takes an image. And it can take that distorted image of Neptune and turn it into something almost as sharp as you would get with a spacecraft or a space telescope. Still not enough to see planets. So here's a sharpened up image of a star taken with the Keck telescope in Hawaii, but underexposed. So all I see is the star. If I'm going to see a planet, I better take a much longer exposure. I better overexpose the star. And when I do that, I still get an enormous messy blob. It's basically lens flare. It's imperfect correction of the atmosphere. It's light scattering off of imperfections or structures in the telescope to produce a swamp of light that's about 1,000,000 times or 100,000 times, only 100,000 times fainter than the star. And that turns out to be way too bright to see Jupiter. Jupiter is 1,000,000,000 times fainter than the sun. Jupiter is 10,000 times fainter than the faintest of the streaks in this image. And so to find planets directly, we cheated. We looked not for planets quite like Jupiter, but for baby versions of Jupiter. It turns out when a planet forms, a process we still don't really understand, that releases a lot of energy. Right now, Jupiter has a temperature of about -200 degrees. But when Jupiter was newly born, it had a temperature of about 3,000 degrees. And then it spent the next few 100 million years cooling off. If you looked at Jupiter when it was young, when it was 100 million or 10 million years old, it would actually be noticeably glowing, and especially glowing in what we call infrared light, the kind of light that hot objects like to emit. And so over the past decade, several groups, including the group I collaborate with, have been looking at young stars, because it makes sense that young stars would have young planets, to try and see if they can find young giant planets. And early in this process, you always get your best results early in a process like this. We had a spectacular example. This is a star, again, boring names astronomers tend to give, called HRID 799, with 4 planets orbiting around it. HRID 799, B, C, D, and E. A, by historical convention, is the name for the star itself, by the way. But this is real. This isn't an artist's conception anymore. This is actual data coming off the telescope. In the center is the star, and there's a little bit of lens flare left over in spite of all the image processing and all the adaptive optics to get rid of it. The star is bigger than our sun. It's about 50% more massive than our sun. It's about twice as hot as our sun. But the other 4 dots are planets. They're 5 to 7 times the mass of Jupiter, and they have a temperature of about 1,000 degrees. This outer one, you can see, looks a little dimmer. It's only about 900 degrees and 3 to 5 times the mass of Jupiter. It's an entire planetary system with its own mega giant planets orbiting around a star. And since we've been watching it for 10 years, we've actually managed to watch those planets orbit. This is 10 years worth of data, an animation put together by Jason Wang, now at Caltech, and Christian Miroir in Canada, the co-discoverer of HRD 799. And this is real data. It's not a simulation. It's a real movie of planets orbiting. And they're obeying Kepler's laws. The planet out here at long distances is going to take a long time to go around the star, perhaps as much as 1,000 years. The closest planet is still going to take about 40 years to go around the star, but they're doing exactly what Kepler predicted. If you'd shown this to Kepler, he would recognize it as a planetary system without even a moment of hesitation. If you'd shown this to Galileo and explained the timescales, he would have realized he was seeing a whole other system, the same way he was the first person to see another system looking through his telescope. These images were humanity's first direct glimpse of another entire planetary system. We also had artists' conceptions to go with the cool images and the blobs. And there's a bit of artistic license in it, but not completely. Because we can see the light from the planet, we can feed it into our spectrographs and we can measure that composition I was talking about. We can tell that the planet's atmosphere contains hydrogen and water and methane, which means it probably does look something like Jupiter. We can see extra infrared radiation from dense hot gas and maybe even from clouds of liquid metal deep in the atmosphere at temperatures of thousands of degrees. And we can tell that those clouds don't completely cover the surface, so that we see bright and dark regions, not at this level of resolution, but that the planet has a complex structure and maybe even weather going on. So it's pretty awesome, but it's still different than our solar system. The 4 HRD 799 planets and a few others that were discovered through direct imaging are really not just like Jupiter. They're bigger than Jupiter and they're much farther out. Something that made this system made 4 giant planets with maybe 20 times the total mass of planets in our solar system. What we'd really like to do next is see something like Jupiter, and we can't quite get there. Even with the fancy adaptive optics that we had 10 years ago, the star is too bright. And so the next step beyond that was the construction of an instrument specially designed for this planet imaging called, somewhat unimaginatively, the Gemini Planet Imager. There's a robot and a fox, for reasons we'll talk about later, for scale. It's not a huge instrument, but it was, at the time we commissioned it, the most advanced extrasolar planet imager built. It had an infrared spectrograph because we want to not just discover these planets, we wanted to figure out what they're made out of. It had a very advanced adaptive optic system that can correct atmospheric distortions with precision equal to about 10 times the size of an individual atom, 1,000 times per second. It had special masks to block that lens flare, that starlight that I'll talk about in a moment. And it had a very sophisticated set of software to connect all the pieces together and a mechanical structure to hold it all together. The masks that block the starlight are referred to by astronomers as coronagraphs because they were actually first invented to block the light from a particular star, from our sun, so that we could study our sun's halo, the corona around it. Of course, corona is a more complicated word to use these days. The masks work by focusing the light of the star, you can see on the right, on a gold-coated mirror, so that the star basically falls down a hole in the center of the mirror. The planet off to the side bounces off the mirror and its light makes it into our spectrograph. We put this instrument together at UC Santa Cruz under construction in a clean room, not clean at this point. This is just when we're initially assembling it, with a lot of help from collaborators, including Les Sadelmeyer on the left, who passed away several years ago after we had finished the instrument project. This is the final piece going in, the infrared spectrograph being lowered down into the structure of the instrument. Once we completed it, we hooked it up to a crane because we're going to bolt this to the back of a telescope. It has to work as it tilts all over the sky. And so we made sure that when we shook it, that no bolts or screws fell out. And then when they did fall out, we found them and reattached them and made sure it didn't move anymore. It has to work on a mountaintop that's cold. So we built a giant meat locker around it, chilled it down to freezing temperatures and then back up again, and saw if the computers and the sensors continued working. We packed and shipped it up almost 7 years ago now for its deployment into Chile. My assistant helped with the process of loading it onto a truck, and then we drove it not all the way to Chile because you can't drive to Chile. Flew it on a land airplane down to Chile and deployed it on the mountain. At which point we sort of picked up our mascot, the Zorro or Clupeo, the Chilean Andean fox that tends to hang around the observatory and especially the observatory diner. Then I flew down and was reunited with the instrument. We put it on the back of the Gemini telescope and had what we astronomers refer to as our first light, our first set of observations, again, with help from the mascot. This is one of the early first light images. It's a little complicated to see, but what you're seeing is that hole that I described, the star falling down with it, and a little bit of starlight glinting off the edge of the hole. And a dot next to it that represents another extrasolar planet, one that we already knew was there, because for your first image, you want to look at one you know you found. It had been discovered by a different Gemini instrument, actually been discovered by the European Very Large Telescope, but this is an image with a different Gemini instrument a few years before we deployed, except that that image represents nearly an hour of observation with a telescope, and ours represents approximately 60 seconds. If we actually spent an hour looking at it and half an hour looking at it and processed all the data, the Gemini Planet Imager GPI was about a factor of 10 more sensitive than its predecessor instruments. So we started a large-scale survey to look at 600 stars and see which of them had young Jupiter-like planets to understand how common Jupiters are. It's been an honor to lead an extraordinary team of scientists who carried this out. We put together, in addition to the instrument, a complex and fully automated data infrastructure that allows every image we take to be turned into scientific data essentially in real time, popping up on our Slack chats, our Zoom calls and such like. And we looked at 600 stars. This is a video showing all, to be precise, 586 stars that we looked at over the course of 5 years. You can see the images we took going by. You can see noise in the images, but you can also see occasional real dots showing up. Most of the dots you see with your eyes are not planets, they're brown dwarfs or stars. And occasionally you might see rings flashing by or sharp edges or lines. Over the course of the survey, our first planet we discovered, 51 Eridani b, was close to Jupiter. It's sort of the most Jupiter-like of any of the planets that we've ever imaged. And then we completed the survey about a year ago. There we go. Before I talk about the planets, if you saw things that look like rings going by, that wasn't an illusion. What you're seeing are what we call debris disks, which are basically asteroid belts or comet belts. Our own solar system has a bunch of comets in it, orbiting beyond the orbit of Neptune, around where Pluto is, in something we call the Kuiper belt. Other solar systems have those too. And in fact, in these young solar systems, those cometary belts have hundreds of times more comets than we do, and they're chaotic. The comets haven't settled down into nice placid orbits, and so they're all colliding with each other. And those collisions produce dust and debris that we can actually see. So around more than 30 stars that we looked at, we saw the equivalent of young asteroid or comet belts. We also saw planets, but nowhere near as many as we thought we would. The top shows 6 planets observed by the Gemini Planet Imager, including HRD 799, which we knew about before we started. But we didn't cheat. We looked at stars based on a computer algorithm rather than looking at stars we knew had planets. But out of 600 stars, we only found a total of, saw a total of 6 planets. At the bottom are objects we call brown dwarfs, which are sometimes thought of as failed stars. They're almost but not quite as big as a star, not big enough to shine on their own to burn nuclear fuel, but much bigger and brighter than a planet. The planets we did see, not quite at the Jupiter separation, but close to it. From those detections, we can at least learn a few things again about how common systems are. We think, combining our observations with the people who do Doppler observations, with the people who do transit observations, that stars like the sun, maybe only a quarter of them or less, have giant planets like Jupiter. Another way in which our solar system is rare is we got to have a big giant Jupiter-y planet anywhere in the system, let alone in the outer part of the solar system where one might argue it would belong. And in fact, where we did see giant planets at all, they were all around bigger stars, 50% bigger than the sun. So bigger stars appear to be able to form bigger planetary systems, which kind of makes sense, but is important for understanding the context of planets. And then finally, the brown dwarfs, the objects 15 to 70 times the mass of Jupiter, are really rare, and their orbits look very different than planets. Somehow planets and stars form through a different process. On the other hand, we didn't quite reach the sensitivity where we could see an exact equivalent of Jupiter. And so we're in the process of understanding what limits GPI and makes it better. We've done modeling to show that, for example, one of the major limiting factors is the jet stream. The turbulence that goes over the observatory caused by the jet stream moves so fast that even at 1,000 times a second, our adaptive optic system can't keep up with it. And so having finished our survey, we're in the process of upgrading GPI to something we unimaginatively are calling GPI 2.0, a faster computer, a better adaptive optic system, better coronagraph masks so we can see planets close to the star and go searching for real equivalents of Jupiter. In the process, we'll likely move it to the Gemini North Observatory on Mauna Kea, which is a complicated situation because the indigenous people of Hawaii are currently not happy about the presence of observatories on their mountain. The long-term fate of that is unclear. Whether GPI will be deployed in the short term is something that we all have to struggle with. Even with this, though, we're still sort of detecting, like I said, giant young equivalents of Jupiter at relatively large separations. The next step beyond it is not to see the young Jupiters, but to see old Jupiters, planets that are really like Jupiter, that aren't glowing, that aren't hot anymore, really the equivalent of our own solar system. And to do that, we're going to have to move from the ground to space. The next chance we have to try it is the Nancy Grace Roman Space Telescope. A few weeks ago, this was known as WFIRST for the Wide Field Infrared Survey Telescope. It's a NASA telescope that's really intended mostly to do the kind of science that RISA does, to study galaxies on an unprecedented scale, to image a huge fraction of the sky and look at literally billions of individual galaxies. But as the next major modern space telescope we're deploying, it's going to be our first chance to put this coronagraph technology into space. It will carry the coronagraph masks that block starlight. It will even carry a deformable mirror, not to deal with atmospheric turbulence because it's above atmospheric turbulence, but to correct for tiny polishing errors in the telescope's mirror and for the way the telescope changes and breathes as it's out in space. It's not perfectly designed for this, and so simulations show it'll probably barely be able to see a small number of Jupiter-like planets, but it will test our ability to image planets in space. On the left are images of a star with light leaking around the coronagraph. On the right are images of a star that has planets. And if you squint at them, there are a couple of lumps that are present in the right-hand image that aren't present in the left-hand image. If you then move over to the far right, it's basically removing all the leftover light to try and reveal the planets. And in fact, in simulations, at least, we'll be able to study planetary systems that are mature, that are like our own. The next steps past that, though, coronagraphs are kind of complicated beasts for attempting to study other planets, other stars. And they're not how you do it in normal life. So imagine for a moment, I can get my assistant to help with this too, that there's a bird flying next to the sun, something really bright, and you want to see it. What do you see? No, you can say here, just what would you do if you wanted to see a bird next to the sun? Yeah, you'd sort of cover your eye. You'd hold up your hand probably as far away from you as you can, and you kind of squint around the edges of it to see if the bird is visible, blocking the light. You don't have tiny little masks and deformable mirrors in your eyeball that refocus light and block it internally. There's a concept called a starshade, which is basically the same thing, a star, and let you see a faint planet next to it. It wouldn't be shaped like a hand. Instead, for complicated optical reasons, it would be shaped more like a flower. A full-size version of a starshade might have to be 30 meters across, 330,000 kilometers away from a telescope, and the two of them would maneuver in formation so that the telescope could see just around the edges of the starshade and see the planet as it becomes visible. Concepts for this, I'll talk about at the very end of this talk, are under development by NASA as potential next future missions that could have the sensitivity to see Earth-like planets. It's also incredibly complicated. We don't have rockets that are 30 meters across, so the starshade has to fold up like origami to fit within a conventional rocket and then unfold in orbit to reach the point where it can successfully block the star. You have to maneuver them very precisely. You have to line them up within, even though they're 30,000 kilometers away, to within about 10 centimeters of where they're supposed to be so that the telescope stays in the shadow cast by the starshade. And then when you get tired of that star, you have to move one or the other so that you can align the whole formation to look at a different star and see what it looks like. There's a school of thought that before we deploy a full-size version of this, it might be nice to deploy a small prototype. And so we've actually put together a project at Stanford for a miniature version of a starshade. Instead of being 30 meters across, it would be 3 meters across. Instead of being 30,000 kilometers, it would be 500 kilometers away. And instead of feeding a telescope like the Nancy Grace Roman telescope that's 2.4 meters across, the size of Hubble, it would feed a telescope that's about this big, that's 10 centimeters across. So that mission we call the Miniature Distributed Occulture Telescope, or MDOT, and it's a subscale or a CubeSat scale demonstration and science mission that could be deployed in Earth orbit to check this technology. This is a collaboration with Simone D'Amico, who's a professor in the Aeroastro department at Stanford, and together with our students and former students, Adam Koenig and Alex Medurowitz, as well as NASA Ames Research Center, who did the design work I'll show, and the Tented Corporation, which does starshade design. The basic concept, small missions like this, one of the things that has changed, for better or worse, in the past decade, is it's a lot easier to launch stuff into space. And so even quite large spacecraft can be carried along as auxiliary payloads while a communications satellite is being launched by, say, SpaceX. So MDOT would be carried as a secondary payload here, deploy from a ring attached to the booster rocket, and then unfold its starshade and deploy its telescope. They'd spend about 4 weeks maneuvering so that they get far enough apart, and I'll show how they orbit in a moment, and then about a year doing science. And when they're doing science, they actually only get to observe a target for about a day, followed by about a month as the formation realigns itself on the next target. And then, because it's bad to litter, we would crash the spacecraft back into some unoccupied part of the Earth, like the Pacific Ocean. The clever bit, which is really entirely Simone's concept, is that the two spacecraft would be in orbits around the Earth's pole, what we call polar orbits. Those orbits cross, the spacecraft get very close to each other at the pole. They don't collide with each other. Only when they come down to the equator are they far enough apart that you can see around the edge of the starshade and see a planet. It takes about 90 minutes to make an orbit, and so they're only in a position to do science for about 5 minutes out of the 90. But orbit after orbit after orbit, you get a 5-minute snapshot of your target star, maybe about 10 to 12 of them before you can't stay lined up on it anymore, looking at a star and seeing with the star blocked by the starshade and the tiny little CubeSat telescope observing it. Again, with a 10-centimeter telescope, you're not going to see a planet like Earth. And in fact, you're not even going to see a planet like Jupiter. This mission is specifically designed to look at that dust from collisions, from asteroids and from comets, from comets and asteroids. The GPI images were really of the outer parts of solar systems beyond the equivalent of Pluto, where comets are colliding with each other and making dust that GPI will live. Our solar system, of course, has not just comets, but asteroids that orbit close to the Earth. And in fact, in our solar system, those asteroids collide with each other, and comets close to the sun add in dust to make something called zodiacal light. I don't know if anybody has ever seen this. I'm not set up to see you all virtually raise your hands, but if you're ever somewhere incredibly dark, somewhere with no moon, somewhere miles and miles away from cities, of course you see the Milky Way. But if you're very careful, you can see another band of light coming up from the horizon where the sun just set, along the direction of the constellations of the zodiac, which is why we call it zodiacal light. And that's the dust from asteroids and comets grinding up in our solar system. And although it's faint to your eye, it's actually the second brightest thing in our solar system. It's 100 times brighter than Jupiter if you add up all the light from it. But so faint that even the Gemini Planet Imager, even the Hubble Space Telescope can't get down to the levels of sensitivity needed to see it. MDOT will be sensitive, not quite to solar systems like our own, but if there's solar systems that have, say, 3 times as many asteroids as we do, or 10 times as many comets, we'd be able to see the dust from them. And these are simulations of a star Epsilon Eridani, which we happen to know actually has about 10,000 times as many comets and asteroids as our solar system does. And so the MDOT mission will be able to map out maybe a ring of dust far away due to comets and a blob of dust close in due to asteroids. And then in my last 5 minutes, let me talk about the future beyond that. Astronomers are in the process of thinking about how, though, we really could reach that level of sensitivity to see Earth-like planets. There's a couple of missions that astronomers have proposed. The first one is called the Habitable Exoplanet Observatory. It's a concept for a 4-meter space telescope that actually has both a coronagraph and a starshade. They work well together. The starshade is good if you want to look at the same star for weeks to study it in detail. But if you want to look at a new star, you have to be very patient. You can move the starshade, then you can let RISA use the telescope to look at galaxies while you're waiting for the starshade to realign. But if you have a coronagraph, you can actually look at a few other stars in between. Combining those and focusing, the mission is designed really to focus primarily on exoplanet science and reach the sensitivity level needed to see Earth-like planets. Beyond that, there's a concept for something called the Large UV Optical Infrared Telescope, or LUVOIR. It was another design study that was really unbounded to look at the biggest telescopes we could imagine with current technology that are technically feasible. An 8 or even a 15-meter telescope, huge compared to Hubble or even the James Webb Space Telescope. Carrying a coronagraph, it's actually too big to work with a starshade. Designed for exoplanets, designed to study the formation of the first galaxies, designed to study how galaxies evolve, designed to map out the universe on enormous scales. And to give you a sense of what it would look like, this is a movie that the California Academy of Sciences made for a planetarium talk I did. This is the Hubble Space Telescope. It's not normally planted at Earth, of course, but it's there to give you a sense of scale. And this is LUVOIR coming into the field of view. For copyright reasons, we could not use the appropriate music for it, but I'm sure you can all imagine it in your head. And so at least on paper, we have the technology to imagine telescopes immensely more powerful than Hubble or James Webb. And those are the telescopes we would need to study other planetary systems on a scale that would let us look at hundreds of stars and see if they have Earths. If they do, we might get an image like this. This is a simulated HABEX image from the HABEX mission design study showing a comet belt, but also 5 whole planets. Looking at the planets, you can't tell which one's an Earth, which one's a Jupiter, or anything like that. But these new space telescopes are designed again to take spectra, to look at the chemical fingerprints. And in some of them, we would see a chemical fingerprint of things like methane or carbon dioxide or hydrogen. But around one of them, we might see a chemical fingerprint of oxygen, of water, and of ozone, of the chemicals we think that on Earth are the signature of life. So it's possible with the technology that we've developed, we'll take that image 20 years from now and see not the red fuzzy dots we see with GPI, but a little blue dot that has a spectrum like Earth. But it's also possible we'll do that and we won't, that we'll look at 200 stars and we'll discover that, again, our solar system is rare to the point of being unique, that there are no other planets like Earth. And in some ways, that would be as important a discovery as finding life around them. And astronomers, no matter what any of us tell you, don't really know which outcome is more likely. Personally, I tend to be on the pessimist side. I think the combination of circumstances that made Earth was astonishingly rare, and that we might look and not find anything except for understanding how our own planet came to be here. If we do that, that emphasizes just how important this planet that we're standing here on is, that the intelligent life that we're frankly doing a terrible job of protecting, as well as the non-intelligent life that we're doing an even worse job of protecting, might actually be unique on the scale of our entire galaxy. And so we need to do something to do our best to look after it. And at that point, I think I will stop my screen share and be in a position to take some questions.
Wonderful. Thank you so much, Bruce. That was great. So please, again, feel free to ask your questions either through the Q&A or through the YouTube channel or through the Google form. I'm going to start with a question about the instrumentation. About the starshades. The question is, how difficult is it to keep the starshade flying in the correct formation with the telescope? And maybe you could answer that both for your tiny version and for the bigger version.
It's pretty challenging. The tiny version alignment tolerance is about 10 centimeters. So you have these two things 300 kilometers apart that stay accurate within 10 centimeters of each other. The large version actually can be all over the place. They can be out of alignment by half a meter or something, a foot or so, but they're 30,000 kilometers apart. On the other hand, some of you may have watched Sunday 2 spacecraft dock with each other, and they did not smash into each other and break apart. And in one docking mode, they used fully autonomous navigation to tap into each other so gently that the astronauts on board the Dragon capsule barely felt the impact. So on Earth orbit scales, we can use things like global positioning satellites to measure positions of spacecraft relative to each other at something approaching the 10 centimeter level of accuracy. The full-size starshades, one of the many things that makes them hard is you can't do them in Earth orbit. If they have to be 30,000 kilometers apart or 50,000 kilometers apart, the Earth kind of gets in the way, or the moon and its gravity. So they'd be millions of kilometers away from Earth. GPS, it's very hard to get a GPS lock when you're a million kilometers away from the Earth. So they would use combinations of optical beacons, of lasers on the starshade, and the light from the star kind of leaking around the edge of those petals of those starshade to measure the relative positions of the two of them. And at least in simulation and in laboratory tests, the technology for that works. But that's another reason why we think it might be a nice idea to test this on the 3-meter scale before we test it on the 30 or 80-meter scale.
Fantastic. So someone asked, how long does it take to build the machines which take these images? And that might have a different answer depending on which images we're talking about, but maybe you could just say a little bit more about that.
Okay. It took us almost 10 years for the Gemini Planet Imager to move from being a drawing on a whiteboard to actually having first light on the telescope. Several years of doing detailed design, 6 months of arguing with lawyers about what the contracts were going to look like, and then assembling all the pieces, bringing them together at Santa Cruz and putting it together. So it was about a 10-year project. It was a big chunk of my life and of the enormously talented collaborators and students who on to be faculty members themselves and who built it. And in fact, it's that generation of people who were our students and postdocs who are now leading the GPI-2 upgrade, who get to make the instrument better for its next set of capabilities. Space missions can be up to 20 years, both due to the sheer technical complexity and due to the funding complexity, the rate at which the government allocates money to try and construct them. The James Webb Space Telescope is going to launch about 21 years after it was a sketch on somebody's whiteboard. These next generation planet imagers might be more like 15 years. The CubeSat we could do in 4, one of the nice things about small scale space missions.
So relating to your question, or your comment about how common the Earth is, someone asked, if we were using the technology we have today and we looked at our solar system from a different solar system, which planets could we detect? And I assume that depends on how far away we're talking about.
Yeah. Well, even at the distance of the very nearest star, the only thing we could tell is there is Jupiter. And we could only do that through the wobble, through the motions of Jupiter. If through an astonishing coincidence, our solar system lined up so somebody else was looking at it exactly edge on, they could maybe see those transits. One star in a million will be lined up so they get to do that. And their version of Kepler would have seen the Earth transit once or twice, and they'd be arguing right now about whether that was a real event or just a bird flying in front of the telescope. So our solar system is nearly undetectable with the techniques that we have right now. The Nancy Grace Roman telescope, I didn't mention this, but it will use a 4th technique to discover extrasolar planets, where the gravity of the planet bends light around the star, something called microlensing. That actually does have sensitivity to Earth-like planets. And so by the end of it, we might have a better answer to how common systems like our own are.
Yeah, so we had another question about what is your best guess on when we can image an Earth-sized planet, or which instruments will be able to do that well?
The capability to really image an Earth-sized planet that's doing what the Earth is, so that's orbiting around a sun-like star, where be in a nice 1-year orbit, and that really is these future space missions. And so they have not been selected. Astronomy is actually involved in a process to decide what our research priorities are for the next 10 to 20 years. I'm involved in that process, which makes it hard for me to speculate about its outcomes. We certainly have the technology, and so it's a choice among both the scientific and non-scientific priorities, whether we choose to do it. But if we make that choice, it's still something on the order of 10 to 15 years before we're going to have the technology in place to do it. I don't know if you're muted, Risa, or if we just have an audio glitch.
There we go. Yeah, sorry. Someone was curious about the temperatures of planets. So are the temperatures that you're talking about, are those surface temperatures? And if so, in that context, how does that compare to the temperature of the Earth?
Right. So the planets we find, like I said, we cheat. We're looking at them when they're really, really hot because they're young. And also they're planets like Jupiter. So they don't even really have a surface. They're really just huge balls of gas. And so the temperature we're quoting is kind of the temperature of the clouds on the planet, where it gets thick enough that we can see the radiation from them. And that temperature is something on the order of 1,000 degrees Kelvin, which is like 700 degrees Celsius, which I can never convert to Fahrenheit, but is probably something in the 1,500 degrees Fahrenheit. So lava temperatures by Earth-like standards. We're really only barely reaching the point where with transits we're discovering a few planets that could have the same temperature as the Earth, but of course we can't measure their temperatures because they're too small and faint right now.
All right. We had a question about the microlensing. Is that the same as gravitational lensing, or is it some application of it? Or tell us a little bit more about that.
Okay. I should say we'll almost certainly have talks about gravitational lensing because it's a thing that kipac does on a much larger scale, what one might call macro lensing or mega lensing. It's just a specific case of gravitational lensing where instead of a whole galaxy bending the light and making distorted images of another whole galaxy behind it so that you see these warped ring-like galaxy shapes, the tiny little gravity of a star, micro by galaxy astronomer standards, is warping the light of another star. And because the warp is so small, you don't see the star's image get distorted, you just see the star get brighter or fainter as the light is amplified by the lensing, by the bending of gravity.
Great. One more question about the star shades. Could you say a little bit more about the star shade? Why is it more efficient if it's depending on where its distance compared to the telescope?
Yeah, there's a complicated set of things that determine it. You can't have the star shade too close to the telescope because then it would just block the planet. Things with hand. If I put my hand here, I'm not seeing the bird around it. You try to move your hand to arm's length so that you can get the most blocking and the most seeing around the edge of it. But it also turns out you can't put it too far away. First, for a sort of practical reason, this formation flying gets harder and harder the farther apart the two of them are. You have to use more fuel. But also for a complicated optical reason, it turns out that even opaque objects like hands and star shades don't cast perfectly dark shadows. Light is a wave, and waves are very sneaky. Waves of light sneak around the edge of my hand, and if I had a sufficiently sensitive camera, I would see a little bright spot in the center of my hand from waves of light coming around the edge of it and interfering with it. That's why the star shade has that complicated feathered shape to reduce the waves of light going around the edge. But even with that, if you move the star shade too far away, light just leaks around the edge of it almost completely and you can't see the planet again. So there's an optimization, a just right distance to put the star shades at, and that sets this scale of tens of meters across and tens of thousands of kilometers away. In spite of which, when it works, it's still really efficient. You don't block any of the light from the planet, so you get every photon from the planet, almost no photons from the star, which is more efficient than our coronagraphs with current technology.
Okay, great. I'm just gonna give you one more question, which is, what is the one thing that you'd call a breakthrough in space exploration in the next decade? Or you could also interpret that as the space exploration needed to study extrasolar planets.
Yeah, I mean, yeah, it's a broad and complex question. What's going to happen over the next decade, and there are different answers in different fields of space. There are people who believe a priority should be sending humans back to the moon, which is certainly potentially exciting and might happen on a decade-long time scale. There are going to be missions to explore planets in our solar systems, a little bit longer than a decade, but one of my personal favorites is a moon of Saturn called Titan, which probably doesn't have life on it, but is full of incredibly interesting complex chemistry and clouds and lakes of methane. And Mars gets all the publicity, but Titan is way cooler. And we're going to send a helicopter to it, which is a pretty awesome technological achievement. On the astronomy side, in the next decade, we're not going to get the planet imagers that I talked about, like I said. And so the big thing will be the James Webb Space Telescope, which again, we could spend a whole separate kipac talk talking about the capabilities it will enable. It will study planets through transits, and it will do that around hundreds of stars. And so we'll get hundreds of spectra of giant planets like Jupiter and start to understand their history and their composition. There's a tiny chance it will get an Earth-like planet. It's got maybe 3 or 4 of the very smallest, very closest stars with planets around which it might get lucky. I'm the pessimist, so I tend to believe it won't. But either way, I think it's the discoveries coming out of James Webb will probably be the most exciting discoveries on a decade timescale in astronomy. And can't really say what those discoveries are, because discoveries, if we knew what they are, we wouldn't be out there making them.
All right, wonderful. Well, thank you, Bruce, and thank you to our entire audience for joining us today. This was really great to learn about. And we will resume with another talk in 2 weeks. I am going to be giving that talk, and then we're going to have several other faculty, postdocs, staff members of KIPAC giving talks roughly every 2 weeks. So please feel free to join our mailing list if you'd like to hear more. This was great, Bruce, and thank you everyone for joining.